I'm from Amsterdam, and I work at KLM, the Dutch airline. My background is in business analytics, which is basically a combination of computer science, mathematics, and a little bit of business sprinkled on to solve specific type of problems. And today I'm here to introduce you to SimPy, which is a Python package for discrete event simulation. For the overview of my talk, first I'm going to introduce a case. You work for Spacey and you need to implement a new factory. And we will use that to look over the different components that make a discrete event simulation and how to implement it in SimPy. We'll go into discrete event simulation itself. What is it? What can you do with it? Then we'll go a bit into SimPy, look at the different components, and end up with some analysis, which is the goal of the discrete event simulation, to measure our performance of our choices that we make. So, the Spacey UFO factory. Your boss, Milan Usks, has asked you to implement a new factory where the idea is that we get orders at any time. It's a build-to-order factory. And the goal is to end up with some completed UFO. We don't start from scratch. We have like half finished UFOs that go into some assembly line where we need to assemble an engine and a dome, and then we can deliver to the customer. All of this is a 24/7 process, so orders can come in whenever, and we are being judged by how long the throughput is from the order until we can deliver. So we will talk about the assembly line portion. Basically, when an order comes in, we have this half-finished UFO, and it needs to go into the engine assembly. However, we have a limited amount of surface stages in the assembly, so that means we can only, in this case, visualization, we can only assemble 3 engines at a time for different UFOs. So sometimes the UFO has to queue up. After this, when there's a spot free, the UFO enters the surface station, and we need to get an engine from the storage, which will then be put in place. It's a similar situation with the dome. It just queues up to the next one. We have a storage. However, sometimes things can go wrong. I don't know if any of you have worked in a factory, but these machines are pretty fragile. So sometimes things break, and that will really disrupt the operation because it will increase queues. And basically, in this case, all we're interested in is the queues that accumulate, utilization of the resources, and, for example, our restocking policy for the storage. So we also have a mechanic station where if something breaks, a mechanic will be requested. He or she will go there, fix it, and meantime we're delivering at the other servers as well. So this is, and there's many places where we can make decisions, right? And the goal is to make these decisions and see what the impact is on our final KPIs. And so we can change the parameters. So that is basically what discrete event simulation is. Discrete relates to the events. So events happen like bam, then an event happens, then an event happens, and but the time is actually continuous. So but it's like, okay, in 13.5 time units this will happen. That's the idea behind discrete event simulation. And we basically simplify our real world to only focus on the things that we understand and that are relevant for our problem, to simplify, so it's a simulation of our reality. And we do that by using stochastic probability theory, where we can model our individual parts, where, for example, our arrivals, they're random, we don't know. So we simulate that by sampling from these probability distributions. Examples where this is used a lot are call center optimization, because there the phones, it's random when they come in. Boarding of airplanes, what kind of strategies should you use? Hospital scheduling, so how much spots should we leave open for urgent cases? What is the probability if we do it like this that somebody will not be able to get the help that we need him, and how much will it cost? And factory assembly lines, so that's the case that we will look at now. And why do we do that? Well, there's many configurations that we can choose, and analytical solutions are available for very small problems, like one queue with one server. Under some assumptions you can calculate directly, but as soon as it gets a bit more complicated, then you cannot do this anymore. And it's specifically useful when we understand the small parts, all the small parts of our operation, but the process interactions between them get really complex. So, and the reason I'm talking about this is because SimPy is a package that allows you to model this, and I think it's a very elegant package. I don't use it a lot in my work, maybe once or twice for a project, but I just think it's a really nice thing, so I've been playing around with it a bit. And it helps you with a number of things. First and foremost, it helps you with bookkeeping of all your processes. All these events that need to be scheduled and happen, and SimPy really allows you to do that properly. It allows for a very hierarchical structure of your processes, and it uses generators to basically generate events and put them on the timeline. And another benefit is that I think it's very well documented, and it has very nice examples to get you started. So now I'm going to talk about individual components, how they relate to our UFO factory and how they relate to SimPy. So our environment is basically what is called our world, our simplified world. So in our case, that's the whole factory. Our environment keeps track of the time, so there's an internal clock, and it also schedules all the events. And what I mean by clock is because the events are discrete, we don't actually use the real clock, but we just skip over to the next event, and then see if that will trigger new things or schedule new events. So but SimPy also allows you to do a real-time one where you have some kind of conversion between your to kind of like, then you can actually print like real-time when a new UFO would come in. But for analysis, it's not that useful. So, and this is how we define an environment and what we can do with it. So first we have to import it. Then we create a new environment. We call it factory here. We can process some kind of process, our custom-made process. We'll get to that later. We can ask for the time. What is the time right now when we're in some process? That's very useful to, for example, see keep track of some KPIs. How long was this UFO in the queue for? How long did it take in total? And with run, we actually start the simulation. So the processes are started and everything is kept track of. So our first process is the order arrivals. Our clients, they want new UFOs, so a new order comes in. And like I said, we have some stochastic element that basically describes how this process happens. And in this case, we're interested in the inter-arrival time. So that is, okay, we have an order, how long until the next order? In this case, it's an exponential distribution. It's used quite a lot for these kind of things. I won't go into this too much, but you can use, for example, SciPy or NumPy to sample from these kind of distributions. And how you fit these, like what distribution should you use? You usually use either historical data from your manufacturer, these kind of things, and to see what is the best approximation of our reality. So we have this distribution and we take a sample from it. In this case it's pretty low, so there's 2.5 time units until the next arrival. Then we take another one, it's another 19, then 7. So this way we fill up this arrival process and we see when will the next order be. I was walking around in Ireland yesterday, and I saw this nice sign. I thought it was very convenient for this presentation, because the way that SimPy manages processes is by using Python generators. Who has written their own Python generators? Okay, we'll do a quick recap of what a generator does. Before we will see how SimPy uses them. So in this case, I have written a count generator. It's not a very useful one, but it's a very clear concept of what you can do with it. Basically, it's a method that you kind of instantiate, and then you can keep asking for the next element, and it's kind of like an iterator. But one of the advantages, for example, of this is that in case of counting, you don't actually need to keep it in memory. You only need, because it only depends on the previous element, we can just store the last element and keep giving the next one. And this yield statement, it's kind of like a return statement, but it just returns the next element every time. So when you ask for the next element, it will keep processing until it sees yield, and then it yields the result back, and then it waits until the next one. So here we start at 0, we add 1 to it, then we yield it, and it returns 1, and then the next time we ask for it, it yields another one. So as you can see here, we kind of instantiate it. I don't know what the right term for it is, but I'll use instantiate, and then we can just use it as a normal iterator, and once we print it, it will print like this. So how does that relate to SimPy? The processes where the control flow happens of your factories, etc. You can you model them as generators, and these generators they yield events, and events is a part of SimPy that we'll dive in a bit later. But it's a really clean way of representing your process, and I think it's very innovative. I've never seen generator uses like this. So we first import stats from SciPy to be able to do the sampling, and we want to do some bookkeeping, so I have a list that we can append these inter-arrival times to. And our generator, this is an infinite generator. It will just keep going. Every time we'll ask next, it will generate a new event. And as you can see here, in the time to wait, we ask for, okay, how much time until the next event? Then we do a yield, and we ask the factory, that's our environment, to generate a timeout event. That basically means, okay, this process is going to be on hold for this time to wait that we just generated. So that means every time the environment basically asks this process, okay, what is your next event? And says, okay, it's a timeout for this long, and then the environment will just schedule that on its timeline, and the next time it will get there, it will just say, okay, now I'll need to know the next one. And here we can, so here we'll keep track of, okay, how long was between every event, and we can kickstart other processes. In this case, it's the process UFO. So, okay, now we've instantiated this generator. How does it look like? Well, we just ask for, we get these timeout events, and the environment knows how to deal with this and how to process that later on when the time is over. Another big part of SimPy is called resources, and there's numerous resources, but the base resource is basically, it's something that you can use, and after you're done using it, you give it back. And in our case, so these assembly service stations, for example, there's 3 servers, so 3 UFOs can use this. They take some time to insert the engine, and then after it's done, it will release the resources again, so another thing can use it. So for queuing systems, this is a very natural way. And as you can see here, we can just instantiate a resource. The capacity is the number of servers, so how many processes can use this service as a resource at the same time. And we can request usage, and that's an event that will trigger the moment that that you're first in queue and a resource releases. So, and we can just ask, like, okay, what is the current user list? What is the current queue list? And then you can see, okay, there's some requests here. And there's 1 in the user because we only had capacity 1, and 2 at queue. And this is this is basically the minimal viable product for this line, this assembly line that we have here. And it uses another kind of advanced concept of context managers. Do you know what context managers are? It's not that important, but basically you can ask for some object, and then once you within that inline statement, you can refer to it. But once you get out of it, it will trigger some things, for example, to close it. In this case, we request this assembly, and then once we're done with it, it will automatically release it again. So it takes care of some of the administration for you, and it makes it more readable. So we have this engine assembly resource. We request a server in the assemble engine process, and then we yield for this request, which basically means, okay, we're going to wait until this request is fulfilled. So there's we wait until a spot opens up. So the environment will know, okay, we can wait until there's place, and then we can go further with the process. Again, we sample some assembly time, so how long does it take? That could be kind of like deterministic in a lot of cases. You could add like, okay, with flip a Bitcoin, and with 5% chance your machine will break, and we need to request the mechanics. And then we do another timeout, because that's the time that the service time that the process will take to go further. And then after this is done, it will automatically release the resource again, because we're in this context manager. Another type of resource is the container. So we have these engines that we need to put in our UFOs, and we need to keep track of this. If we have no engines, the process cannot continue. So in this case, it's just called a container. A container has a homogeneous contents, so it's all of the same thing, but it can be discrete, like with engines, or it can be continuous, like fuel, for example. And we can instead of request and release, we have get and put, and we start with some initial value, and you can cap it, like, okay, it can be a maximum of 40 units, and then the put will wait until there's actually space to put these units in. Here's a small process that you can start every time that you request this to see if we should restock. So the way I've implemented this is we have some Boolean value that kept track of if we already ordered, because else it will just keep ordering more and more, and then our boss will not be too happy with the bill. So if we're not ordering yet, and our engine storage level, so that's just the amount of resources in this container, is below some kind of level, then we're going to place an order. The order will take some time to arrive, so we have to wait for that, the yield, and then we will put that amount into the system. And this is something that we can choose, right? If we put the restocking level too high, then we'll have too much resources laying around, which costs a lot of money. But if it's too low, we run a higher risk of having to stop the process while we wait for our supplies to get there. So this is something that we can inspect, because it's all dependent on all the other parts of the process. We can inspect how well our current strategy works and what happens if we tweak it. So now, if we want this to ask for an engine, we can use a GET request, and but first we will start the restock engine storage process to check if we need to order new things. And you can see here within, so this get engine, below with the with get engine, this is a process. And you can either yield processes, so that means we have to wait for this other process to work, so these processes can also act as events, or you can just start them, and then the current process will just keep going while the other one is also started. So that really allows you for a lot of flexible control flow of your simulated world. So now we've already discussed, named it a couple of times, but events are also an important part. And you can write your own custom events, but there are a few ones that are really important. We've seen a few already. So the timeout event is an event that will trigger in X amount of time. The request will trigger if the resource becomes available for us. And with the normal one, it's just first in, first out. So the one who has been waiting the longest will be the first. But there are priority queues that you can implement, preemptive queues. All of it is in SimPy. There's a get, but also these custom processes that we write, you can also use them as events. And you can do this kind of like Boolean logic with your events. So you can, in the case of the end, then we have to wait for both the events to trigger, and then we can continue. So in our case of our engine assembly, we both need the server to be available, so we have to wait for a place to get, and we have to be able to get an engine. So only if both of these requirements are met, then we can actually start assembling. But you can also do the other way around. You can also have OR, and that basically means, okay, if one of the events triggers, we will continue. And you can check which one of the events triggered. And that could be the case for let's say you have, you model it in a way that your assembly engine will break after X amount of time, and you have a service time, so then you check which one happens first of these timeout events, and then you either go in a different flow. So now, actually, we're using some subroutines that we wrote before. We can model this part of our factory by requesting an assembly, requesting an engine, and then the yield assembly and engine means we have to wait for both of these events to happen. And after that, we're going to actually assemble, and we have to wait some random amount of time before this is finished. I rewrote all this code into a more object-oriented way where we can keep track of all kinds of things. You can find it on my GitHub. Now we're going to look at the analysis part of it, because this modeling is not our goal. This modeling, like the analysis that we can do on this simplified world, is the actual goal. So I want to quickly go over what choices can we make and what errors can we make, and then see how we can use that. So we have to order arrivals. It's pretty easy to use historical data, except for maybe it's a new one. So there we have to maybe estimate from our market research how much orders will we get. In our case, we see it as a constant arrival process, but it could of course matter depending on the time of the day. I don't know how it works in a galactic, intergalactic way, but then we have the assembly line. There we can we kind of know how long assembly will take, but we also need to we maybe not know how often it will break. For the storage, and we have to decide how many servers we actually want to put there. Then for the storage, we can check our restock levels. It's the same for here. And then for the mechanics, we could maybe hire more mechanics, or maybe we want to pay senior mechanics because maybe they're more expensive, but their service time is lower. These kind of things we want to analyze. So in our case, since it's a continuous one, you can just say, okay, I want to run this for a year, and I want to just see what will happen over this year time. And that's basically for one configuration. What you can also do is look at multiple configurations and test like the robustness to your assumptions, or test different configurations of the choices that you make. So here we can see on the x-axis there's the time. So in this case it was 5,000 time units. And on the y-axis you can see, okay, the UFO that came in at that point, how long did it have to wait? So how long was it spent on queuing? So that can give us like an insight in, okay, is it waiting too long, or how dependent is it? You can see here that if, like for example, if there's a bunch of orders coming in at the same time, then the waiting times go sky high. We can look at the distribution of the waiting times. So does this look okay? Well, it's normal that it spikes at 0, because in a lot of times maybe it doesn't have to wait when there's less things, or maybe the machines haven't broken much. And here we're looking at the mechanic station. Okay, at the moment we want to request a mechanic. How many mechanics are working at that moment? So here we can see, okay, only a few times it had to wait, but so maybe that could change our decisions that we make with our hiring. And here's one for the dome stock levels. Okay, so we had every time that we wanted to restock, there's an amount of time in between, and what happened with the stock levels at the moment that our order came in. So here you can see, okay, yeah, maybe we're too conservative at the moment, and we waste too much time on storage space, or waste too much money. Like I said, our main goal is to compare different configurations and make the best decisions that allow for the least risk or the most money. And I have one example here where we look at the arrival rate. So that's our estimate. Rate is actually kind of the wrong word, but the inter-arrival rate. So if you go to the right, less and less arrivals occur. And what we see on the y-axis, in this case, I looked at, okay, how much of these orders were going through the whole system within 100 time units. And now you can see, okay, how much does it matter if we get this wrong? And you can see here that it makes quite a difference. So if I piqued your interest, there's a lot more to discover both on the theoretical level of discrete event simulation and on SimPy itself. Like I mentioned already, there's priority resources that really that can allow you to make different options within your flow. For example, if you get penalties, if it's not finished within 48 hours, maybe you want to prioritize the ones that have been waiting for too long because there was some mechanic involved or something. There's stores, which is kind of like containers, but you can have different type of items in there. You can write your own custom events. It's very extendable. And you, as I mentioned before, you can use real-time simulations. For example, you can bind that to animations so that you can visualize your process, because some people in the business are more about visuals than numbers. And what a nice thing about SimPy is, what I didn't really mention, is because it all lives in your own code, right? You can keep track of whatever you want. You can use like LP formulations to initialize your first things, or you can use machine learning to predict these arrival processes, or these kind of things. It's really integrated into Python, which I think is a big benefit. So hopefully I was able to show you a little bit about what discrete event simulation is about. I was able to introduce you to these first concepts of SimPy. I was able to inspire you to try using this in your work or in your hobby projects. And I hope to help you make Milan Esk happy.